Hello everyone. Welcome to second lecture of CS 531 Memory Systems and Architecture. Today we'll discuss about the introduction of main memory systems or the this memory that we call RAM of our computer systems. So today I'll attach a video that I have recorded last year with after this small clip. So whatever I'll discuss today is not recorded now. It's recorded 1 year back. But since the content is exactly same, so I'm not recording it again. I'm just attaching my previous video here. So please note that since the video is from last year, so during this video, if you find any announcement related to the course, so please ignore it. This is not the announcement of this year. So from now onwards, I'll just note that in this lecture, there is no announcement related to your course. Just concentrate on the concept. But before starting this video, let me remind you again about the weekend tutorial of JAM Simulator. By today evening, I will share the Excel sheet where you have to confirm if you are attending this tutorial or not. Okay. So from this point onwards, whatever I'll explain, it's a recorded video from last year. So do not consider any announcement related with course. Just concentrate on the content, and I hope everything will be clear regarding to main memory. And after this presentation, if anything need to clear from my side, then tomorrow there is a live session. So please join the live session and clear your doubts. Thank you.
When we say about memory in computer, memory means storing some information. Whatever is a memory, it's a hard disk or it's a memory card or whatever memory it is. Memory means storing some information in a device or in a chip. Suppose in a chip storing some information. But we know in computer information means binary content. Information means a sequence of binary digits. Either it's a binary sequence of binary 1 and 0, nothing else. So down the line, storing some information means how to store information means how to store a binary bit. If you can successfully store a binary bit, either it's 0 and 1, then we can easily store any sequence of binary bit. That means any information you can store in computer. So this is the main question is how to store a binary bit. And for this, there are many technologies. So the two technologies that we will discuss today is SRAM and DRAM. And what is cell? The cell means in any technology, the content, this device or the storage required to store 1 bit information is called cell. So this is a SRAM cell. This cell is required in SRAM technology to store 1 bit of information, either it's binary 1 or binary 0. This is a DRAM cell. So this cell is required to store 1 bit of information in DRAM technology. So there are two technologies here. I'll not discuss this SRAM technology in detail because this is not the purpose for this presentation. I'll only say here, if you want to store 1 bit information here in DRAM cell, then you can see how many transistor will be required. There are two transistor you can see here, and these gates, if you want to implement this gate, you need 4 more transistors. So that means six transistor is required here to implement one cell in SRAM, or you can say to store 1 bit of information in SRAM, you need six transistors. But if you see here in DRAM cell, here there is a this is called capacitor. So there is a capacitor and there is only one transistor here. And in DRAM, information are stored in form of charge in capacitor. If the capacitor is fully charged, that means see this is the capacitor. So if the capacitor is fully charged, that means it is binary 1, and if the capacitor is not charged, you can say this is binary 0. So now suppose this capacitor is fully charged, then how you will read this data? To read this data, you have to activate this transistor, or you activate this line. If you activate this line, then this transistor, normally transistor work as a switch. So if you activate this line, this switch will on. The moment this switch is on, then this charge will be available through this line, this bit line. In this way, you can read, you can sense this charge. So now both the design has some advantage and disadvantage. So what is the advantage? So if you go for this, as I said that here to store 1 bit of information, you need 6 transistor. That means it has very low density. Why it is low density? Because suppose there is a small area. So before going this, let me explain here. this has very high density. Why this has very high density? Because to store one bit of information here, you need just one capacitor and one transistor, and here you need six transistor for one bit information. That's why this is low density, this is high density. What do we mean by low density and high density? Low density means, for example, suppose there is a fixed chip area. So within this fixed chip area, if you can place a 4 MB of SRAM memory, then within the same chip area you can place a 6 time higher or 6 time larger DRAM memory, because it has very high density. Lot of DRAM cell can be placed within the same area as compared to SRAM cell, because SRAM cells are larger in size. So in this way, DRAM is better. That means DRAM has larger capacity. Capacity wise, DRAM is better than SRAM. But SRAM is faster. We all know SRAM is faster than DRAM cell. DRAM cell is more slower than SRAM cell, and that is the reason that SRAM we normally use to design faster memories like cache memories, and DRAM cell are mostly used to design comparatively lower memories, slower memories like main memory. Another advantage of SRAM. So before discussing this advantage, we have to say something about in DRAM. So if you see in DRAM, as I said, informations are stored in form of charge. So if information, suppose you stored a binary 1 here, that means this capacitor is fully charged. But even if you are not reading this content from this, then also automatically it will discharge after some time. That means information, it leaks the information or it leaks the charge. So it is not like which is not possible in SRAM. In SRAM, if you store binary 1 here, then this binary 1 will be remain intact here until the power is there. If you are supplying power, then this information will be intact here, which is not the case in DRAM. In DRAM, if in this particular capacitor, if you stored binary 1 by fully charging this capacitor, and if you are not doing anything, and but then also automatically it will leak or it will discharge. To prevent this loss, we have to periodically refresh or periodically recharge this cell or this capacitor, and that is called periodic refresh. That's why if I hope you know that in case of DRAM, we have to periodically refresh these cells of DRAM. Otherwise, this data will be automatically discharged, because the information is stored here in form of charge, which is not the case in SRAM. So this is the advantage of SRAM, that SRAM doesn't require a periodic refresh, and this one disadvantage of DRAM, because it requires periodic refresh. So now let's move to this slide and try to understand the other advantage and disadvantage of SRAM. I think most of these points I already explained in previous slide. Positive means advantage. So SRAM is faster than DRAM. Obviously, I already explained. So that's why this is a positive for advantage for SRAM. Refresh is not required. Again, it's the advantage for SRAM. Lower density requires 6 transistor per bit. That's why this is a disadvantage, because it has, as I explained, SRAM has lot of area overhead, higher cost, or we can say this last point is higher manufacturing cost. So again, it's a disadvantage for SRAM. So here there are, you can see there are some advantages and some disadvantages, and same thing we can see for DRAM technology also. In DRAM technology, the advantages are it has high density and high capacity, so we can design larger size memory with and again it's low cost, low manufacturing cost. So if we combine these two advantages, that means we can design a higher larger size memory, and we can put it in a small chip area with and without increasing the manufacturing cost. And the negative side of DRAM is it needs periodic refresh, and it is slower than SRAM. So if you see the advantage and disadvantage, you can easily understand that why we use SRAM to design smaller and faster cache memories, and why DRAM is used for slower and larger DRAM memories or main memories. Both has their own purposes. Now, if you remember, if in this DRAM cell, I said this particular cell is required to store one bit of information in DRAM. Suppose there are multiple cell here, and they are stored in a particular row like this. So in this case, and there is a line here. So in this case, this line we can say this is a word line, and this word line is connected with all the transistor here. So now if we activate this particular line, or if we activate this word line, then all the switches or all the transistor will be activated. It means if all the transistors are activated, then these charges stored or the information stored in each capacitor will be available through these vertical lines, which are called bit lines. This concept is very important, and you will understand in the next slide here. In this slide, if you see, there is a 2D type of design, and most of the memory, if we know from our basic BTech course, then we know that most of the memory looks like this, a 2D like structure. Most of the memory is a 2D like structure. So here we'll say this is the entry here. This is the entry. This is the entry, same as 2D array. So in 2D array, there are multiple entries. We'll say this is the entry. So each entry has a address like column, row number, column number. So assume that this is R1, C1, row 1, column 1. This is row 1, column 2, like this. Okay. So in memory, most of the time what we see that the smallest unit that we can read or write in a memory is a particular entry. That means this entry. In this particular example, what you can see that in each particular entry there is only one cell or only one DRAM cell. That is only one bit of information is stored, but it is not always true. If we go for a larger design, then that we will discuss today and also tomorrow, that you will see that in a particular entry in the 2D area looks like memory, there may be multiple entries or multiple cells stored here in this entry. But for this simple design, assume that in each entry there is only one cell. So now assume that I want to read row number 1 and column number 1. Row number 1, column number 1 means this particular location or the content of this particular entry. As I said, there is only one bit stored here. That means I want to read either binary 0 or binary 1. So how to read it? So suppose if we want to read row number 1 and column number 1, for example, this particular entry from this memory, then the row address will be first sent. Address of row number 1 will be sent through this line, and this row decoder will activate this particular row. So this particular word line. So once this particular word line will activated, all these transistors will on, and this information stored in these capacitors will be available through these bit lines. And these bit lines are connected with this device or this circuit. This circuit, you can call it as a row buffer, or it's not a column decoder. It's written as column decoder, but for now, just remember that it's a row buffer. So these bit lines are connected with this row buffer. So ultimately the content of all these cells will be available in this row buffer, and with just activating this word line. So when we activate this word line, the content of this entire row is available in row buffer now through these bit lines. This is fine. Now the second is, we don't want the entire row. As I said at the beginning, that I just want to read row number 1, column number 1. So row number 1 is now available in this row buffer. So now I'll supply column number 1 through this line, and this column number 1 will go through this column decoder, and ultimately it will go to row buffer, and then from row buffer I can read the content of this content, and this will come out through this line. So how to read it? First of all, we'll activate this row number 1. Then entire content of this row will be available in row buffer, and then after this I have to supply the address of this column. This column number 1 will supply to this, and then after this the corresponding content of this column will be coming out from this row buffer through this line. This is how the read and write performs. I have not explained write because this is read. In this case of read, data flows from this direction, and in case of write, data flows in opposite direction. This is the difference. And how exactly read and write perform in binary in DRAM cell will be discussed in next slide. Now I'll discuss the structure of main memory, that we also call the RAM of the computer. We'll discuss the structure of main memory or structure of RAM from root level, that is in top down approach. So when we say RAM, and suppose you want to purchase a RAM, then you will go to computer shop, and if you just want to purchase a RAM, then you will purchase this, which is called DIM here. You will purchase this. And if you ever seen any motherboard of desktop, suppose I'm only saying about desktop because I'm not saying about the RAM is there in laptop also, but I'm only concentrating on desktop to explain it properly to you. So suppose if you ever see a motherboard of desktop, you will see there are multiple slots to put this RAMs, or you can say in our term we can say DIM. There will be multiple slot to put insert this RAMs in motherboard. So there may be multiple slots in motherboard. So these slots may be divided into multiple channels. Suppose in this particular case, if you see that, for example, suppose the motherboard I am showing here, assume that there are 4 slots and these 2 slots are in one channel and these 2 slots are in another channel. So, and all these channels or all these DIMMs are connected through a NOT chip, and all these RAMs are connected with CPU through this NOT chip. So this NOT chip is responsible for communicating between processor and all these memories. And this is also the reason that's why the RAM is called off chip memory, because it is placed outside the CPU. See, this is the CPU and it is placed outside the CPU. It is placed in the motherboard but not inside the CPU. But cache memory is placed here inside the CPU. That's why cache memory is called on chip memory. And since this RAM is main memory is placed outside the CPU, that's why it's called off chip memory. So now let's concentrate on only the structure of only one DIMM. And the next slide, I'll only explain the structure of only a particular DIMM. So this is the particular DIMM, dual inline memory module. So now if you see, and this is also RAM, as I said, if you go to market and purchase the RAM, you will purchase this chip. So if you see, there are multiple, there are 2 sides of this is the front side and there will be a back side also for this. So each side is called a rank. So if this, suppose this is shown here, so suppose this is front side of this chip or this DIMM, this is rank 0, and this is the back side of this DIMM, this is rank 1. So, and I'll only concentrate on this is the front side of this DIMM. So if you see the font side of this DIMM, that means I'm saying about rank 0. This is called rank 0. So there are many rectangular boxes here of black colored rectangular boxes. So each of these rectangular box is called a chip. So if you see here in this particular rank, there are 8 chips, and it is also showing here there are 8 chips. So, and same thing will be there in the back side also, that means in rank 1, then rank 1 also there are 8 chips. But before discussing the structure of a chip in detail, let me explain something more about rank. As I said in the previous slide that rank has multiple chips, so this is the more clear picture of a rank. Suppose this is the rank, and now in this rank there are 8 chips, suppose, and all the chips, suppose all chips are connected with a common bus here. So now the question is, why this is called a rank? Why each side of DIMM is called a rank? This is called rank because there are multiple chips, but if there is a command given to this rank, all the chips will work simultaneously on the same command. That means all the chip in this rank will perform the same command, will execute the same command simultaneously. That's why it is called a rank. In this particular rank, it can send 64 bit of information at a time. But suppose this 64 bit of information is not coming from a particular chip. It is equally coming from all these chips. For example, if 64 bit of information is required here, then 64 means 8 byte. So first byte is coming from chip 0, second byte is coming from chip 1, and then next byte is coming from chip 2, and the last byte is coming from chip 7. So together, combining all this 8 byte or 64 bits will be transferred by this rank. That's why it is called rank, because if there is a command of read command is given to this rank, then all the chip will perform this read command simultaneously, and all the chip will send 1 bit of information, and then these 1 byte of information, and then all 8 byte of information will be merged here and then transfer this 64 bit of information outside this rank. Now let me explain the internal structure of a chip. How a chip look like? A chip looks like this. A chip normally has multiple banks. In this case, you can see there are multiple banks: bank 0, bank 1, bank 2, up to bank 8. There are 8 banks in this chip, and all the banks are connected to a common decoder. You can say there is a common bus. So that means if bank 0 is communicating out to the outside world, then at the same time bank 1 cannot communicate because they are using the same shared bus. So only one bank can use this share bus at a time. Then how this bank is given benefit if they are using only share bus, that I will explain later. But now, before this, as I said, this is the structure of a chip. So now let us see the complete picture till now. This is the complete picture till now. I said this is a RAM, or you can say this is a DIM that is available in market, and in both side there is a rank. This is the front side, there you will see rank 0, and the back side there will be another rank that is called rank 1. So if you see only one side, that is this is rank 0, and there is multiple chip. These black side is black boxes are called chip. So there are 8 chips here. So how each chip is look like? Each chip looks like this. So this rank is again designed in this way, and each chip, that's why I say, for example, this particular chip will looks like this. This is the particular chip. So actually inside each chip there are multiple banks. So now how a rank works. For example, suppose if this particular ranks gives a command that read from bank 1, or for example, suppose this to this rank, if I give a command that for example, suppose read from bank 0, that means, as I said, rank means the same command will be executed to all the chips simultaneously. That means read bank 0 means read from this bank 0, read from this bank 0, read from this bank 0, read from all the bank 0 of all the chips will be performed simultaneously. That's why it is called rank. So I hope this is clear. So now the next we will try to understand what is the structure of each bank. Bank you can consider as a 2D memory, that, or this is the classical memory design that we know from our BTech courses, that how a memory should look like. So a bank look like this. It's a 2D memory, and there are multiple entries here. So I'll say this is an entry, or you can say this is a column. This is a column, this is a column, or you can say this is an entry also. So as I said previously, that when I explained about the basic DRAM cells, then I said each column can store only one bit of information. Now I'll not say this. I can say, oh, each entry or each column can have multiple bit of information. For example, here in this particular, I'll say that suppose each, if you go to this design, sorry, this design, in this design, then you have to then we have to say that each column is storing 1 byte of information, or you can say 8 bit of information. That means each entry for this particular column is storing 8 bit of information. So now suppose in this particular case, if this is a bank, and suppose this is a D, and this bank is designed with DRAM technology. As I already explained, that if this bank is designed with DRAM technology, then storing each binary bit, we are using a DRAM cell. So if we want to store here 8 bit of information, then within each column there will be 8 DRAM cells. So now suppose I want to read this now suppose I want to read the content of this cell, sorry, content of this column, that is row number 6 and column number 1. So how to do this? So first of all, a row address will be sent to this, and this row decoder will decode this row address, and only this signal will be activated. So if this signal will be activated, that means this word line will be activated, and if this word line is activated, then all the information of this row will be available to this column decoder or row buffer. Now we'll say it's you can say that this is this is acting as a column decoder as well as a row buffer. Later we'll explain it in more detail. So now once this line is activated, then all the informations of this row are available in row buffer here. But we don't want all this information. We only want information. For example, suppose instead of column 1, we want to read this column. Then we only want this column. So after this, the column number will be supplied through this. And after supplying this column number, this column decoder will allow to pass only the information of this column, this green color column, through this data out pass. And as I said, if based on the previous example, if suppose there are 8 bit of information stored here, then after supplying this column address, these 8 bit of information will be coming out from this line. So this is exactly what we want here. What we want from this chip 0 is that 8 bit of information should come out from this chip 0, right? So this chip 0 And suppose this chip 0 looks like this here. This chip 0 looks like this. There are multiple banks, and suppose this particular 8-bit information that we want from this chip is mapping to this bank, bank 0. How now bank 0 looks like this is now bank 0, and this particular 8-bit information is stored here in this column of bank 0. So that's how it, first of all we have to activate this row, then this row all the information is available in this here in row buffer. And now from these bits, from all this information of all this row, we only want a particular column. So that column address will be supplied now through this. And now after column decoder, then this column, this line, the information of this line will be coming out from this data out. That means it is giving 8 bit of information as required here. The same thing will be performed by all the chips simultaneously, since this is a rank, and if a command is given, read command is given, then all the chips will perform it simultaneously. In this way, finally the rank will get this 64 bit of information, which it will transfer to the DRAM controller. So as I said, this is working as a column decoder as well as a row buffer, but there is another term that we normally use for this, instead of row buffer, is called sense amplifier. So there are, sometimes it's called row buffer or sometimes it's called sense amplifier. So there are two terms, and both will be explained later again. But now suppose, as I said, that first of all I want to access the entries of this particular column. So what we did, I activated this row. After activating this row, all the informations are available in this row buffer or sense amplifier. That is fine. And now supplying this column address, I can read this column address. Fine. After some time, or maybe the next consecutive request is to read this column address, read the content of this column of same cell, same row. In this particular case, we no need to activate this row again, because the content of all this row, all the content of this row is available in this row buffer. So in this case, no need to activate this row again, only supplying the column address of this. That means column number 1, only supplying column number 1 through this line is enough to pass this information through this line second time. But after, I assume that the next access is this location, that means row number 1 column number 2. In this particular case, you have to activate this row again, but before activate this you have to do something, because now in this row buffer the content of this row is available in this row buffer. So before activating this row, you have to close this particular row. After closing this row, you can activate this row. And when we'll activate this row, the content of this row, that is row number 1, will be available in row buffer. And now when suppose you want to read column number 2, then column number 2 will be supplied to this, and the information from column number 2 will be available through this line. How these rows are closing, how these rows are opening, and how this information are storing in sense amplifier, all this thing will be discussed detail in next slides as well as in next lecture. So this is a detailed structure of a main memory. It starts with channel. So in a motherboard of a particular computer, there may be more than one channel also, and each channel can have multiple DIMM. As I already explained what is DIMM, and then each DIMM can have multiple ranks, and each rank has multiple chips. Each chips has multiple bank, and a bank is normally designed with multiple rows and columns, and each entry in this in bank, that means in for example, suppose row number 1 and column number 1, that is called each a particular entry. So each particular entry has multiple DRAM cells if this main memory is designed with DRAM. Now the next thing we'll discuss here is sense amplifier or row buffer. So now onwards we'll say the sense amplifier. So the question is, why we need a sense amplifier? Why it is not possible that every time we'll go and read from a particular row? Why we need a sense amplifier in case of DRAM memory? So if you remember the DRAM cell I explained, for example, suppose this is a figure of DRAM cell. So as I said, this information are stored in the form of charge in this capacitor. That means the capacitor is, if I want to store binary 1, that means capacitor is fully charged. But as I said, if we want to read this information, then this particular transistor will be switched on or this is activated. The moment this transistor is activated, this charge will be available through this bit line, and then we can sense it or we can read it. But it means that if we want to read this information, the capacitor will be discharged. That means even after reading the information, this data is discharged from the capacitor. So this is one particular problem with DRAM cell. Another major problem with DRAM cell is the charge that is stored in the capacitor. The capacitors are normally very tiny capacitors. Then the charge they are storing in this capacitor is also very tiny. And these tiny charges, when they are available to this bit line, this charge is not enough to drive a circuit. Means maybe this if suppose the capacitor is fully charged and you just activated the transistor and the charge is available through the bit line, but this charge is very tiny. Remember, this charge is very tiny and this charge is not enough to drive a circuit. Means it we cannot say that okay, this charge means binary 1, this charge means binary 0. It is very difficult to say. So that means there should be some circuit which can amplify this, which can sense this small amount of charge and can amplify this charge to either binary 0 or binary 1. That's why we need an amplifier and we call it sense amplifier. So let me explain how a sense amplifier looks like. This is how a sense amplifier look like. There is an enable line here. There will be two part, top part and bottom part. So there will be voltage available here. There will be voltage available here. So normally a sense amplifier has two states, two stable state. We can say there are two stable state of a sense amplifier. State 1 and state 0. When I say state 1, the both states are mentioned here. State 1 means if this is VDD and this is 0, that means this is state 1. State 0 means if this is 0 and this is VDD, then it is called state 0. So both states are showing here. So this is an example that sense amplifier is in state 1. That means this is VDD, top is VDD and bottom is 0. This particular and this sense amplifier is in state 0. That means this top is in 0 and bottom is in VDD. So you have to remember that a sense amplifier has two stable state. State 1 means this is VDD, this is 0, and state 0 means top is 0, top voltage is 0 and bottom is in VDD. So I have to remember this, the two stable states, state 1 and state 0. Now the important property of sense amplifier is, suppose there are two voltages here. This top voltage is VT and this voltage is VV. I'm not saying that it is 0 VDD or it's any voltage. Suppose it's any voltage. It's not like I'm not saying about VDD or 0. Suppose this is the voltage VT and this is a and bottom there is a voltage called VV. Now the important property of the sense amplifier is if VT is greater than VV, that means if this voltage, the voltage available here, if this is higher than this voltage, then automatically it will be shifted to state 1. That means automatically it will be converted to VDD and this will be converted to 0. That is written here. So the same thing is written here. It is written here is that if VT greater than VV, that means if this voltage is greater than this voltage, then automatically sense amplifier will goes to stable state 1. Or in another case here it is written that if VV greater than VT, that means if this voltage is greater than this voltage, then automatically sense amplifier will goes to stable state 0. So this is the advantage or this is the main property of sense amplifier, and because of this property we use sense amplifier with DRAM memory. So in this slide I'll explain you how a read operation is performed from a DRAM cell through sense amplifier. As I said that the charges available in DRAM cell is very tiny and these tiny charges not enough to drive a circuit. That's why we need a sense amplifier. Suppose and now how sense amplifier how we can use a sense amplifier to read a DRAM cell. Suppose this is a DRAM cell. I have designed it in in a different way. Suppose this is the DRAM cell and this is the capacitor. This is the capacitor and this is the transistor. So somehow this is the switch. So if we on the switch here, then the charges available here will be passes through this switch and it will be available through this bit line. And if you see that this bit line is connected with the sense amplifier, now this is the sense amplifier. Now how this sense, why this sense amplifier is required and how this will help to read the content of DRAM cell, that will be discussed or explained in this slide. So assume that this DRAM cell, this is the capacitor of the DRAM cell, is fully charged. So now if I want to read this DRAM cell, I have to activate this switch or this transistor, means I have to on this switch. If I activate or on this switch, what will happen? Okay, before discussing this, you have to understand that if you let's see the voltage of this sense amplifier. Both top and bottoms are maintained 0.5 VDD, 0.5 VDD. That means they are the same, maintaining the same voltage in both top and bottom at this moment. So now, before reading the DRAM, this is the scenario of sense amplifier. Now I want to switch on this transistor. So the moment I switch on this transistor, this is fully charged. So some charge will pass through this line. If some charge will pass through this line, then the voltage here will be increased from 0.5 VDD to 0.5 plus delta. 0.5 plus delta. So that's why the moment you switch on this transistor, some charge from here will be transferred through this line, and now the voltage here is 0.5 VDD plus delta, means a tiny increase of voltage shown here in this step. And as I explained in previous slide, according to the property of sense amplifier, now this voltage is higher than this voltage. So this VT is greater than VV. It means that automatically this sense amplifier will goes to stable state 1. That means VDD. So this will, instead of this 0.5 VDD plus delta, ultimately it will goes to VDD here and 0 here, and that is called binary 1. You can say, you can assume that is a binary 1, like this. See, it is automatically it is converted to VDD, and now it is 0. This is stable state 1. Stable state 1 we can sense as a, we can assume as a binary 1. But now what is happening here, you can see that here you can what I said here, when this switch is connected, some charge goes here, but you can see here it is again fully charged. How? Because when some charge goes here, it's become plus delta, and after this, according to the property, since this VT becomes greater than VB, so this automatically converted to stable state 1, and now this is VDD. The moment this is VDD, this charge will again flow from this flow to this direction, and it will again completely recharged. So sense amplifier is doing dual purposes, serving dual purpose here. First thing is, it is allowing to sense this tiny charge through this and converting into stable state 1. This is the first thing. And second thing is that there is the, it is also solving the problem of the second, it is also solving the second disadvantage of a DRAM cell. That means the moment you read the content of a DRAM cell, the charges or the information stored in the DRAM cell is destroyed. And if we use sense amplifier, then after reading this content is automatically restored here. So this is the advantage of that's why we use sense amplifier with DRAM cell. So every operation in DRAM cell means, if we want to read or if we want to write, we need a sense amplifier connected with DRAM cell. Now let us explain how we can read a binary 0 from DRAM cell. So just assume here, I'll show also, just assume here in this particular picture, assume there is no charge in this particular cell. No charge means binary 0. Just assume that there is no charge here. There is no charge here. So if there is no, and again it should be in this condition, half VDD, half VDD, top bottom, half VDD, half VDD. If there is no charge here, and if you connect this switch, and if you connect this switch, then what will happen? Since there is no charge here, and if you connect this switch, some charge from here will flow through this direction. If some charge from here will flow through this direction, then here the voltage will be 0.5 VDD minus delta. The moment it will become 0.5 VDD minus delta, VT will be less than VV, so it will be automatically converted to stable state 0. That means this will be VDD and this line will be 0, which is also, and if a sense amplifier is in stable state 0, that means we can assume it's a binary 1, it's binary 0. So in this way, we can sense that this is the 0 is stored here. Now, if we connect, suppose as I said that there is no charge here and we connect it, then some charge will flow through this line. But since it is zero stored here, this line ultimately becomes zero, then this charge will again flow here, and it cannot do any harm because this is already VDD. So in this way the content of this cell will also remain intact, and this zero is now available in this sense amplifier. So in this way, I explained first. I explained how a particular cell can read binary from how using sense amplifier you can read binary one from a DRAM cell, and how again using the same sense amplifier you can read binary zero from a DRAM cell. But remember that in both cases, before starting the read operation, the status of sense amplifier should be like this: 0.5 BDD, 0.5 BDD. That you have to ensure. First of all, okay. Now next, this is called read operation. How to do write operation? Suppose this is the scenario. Suppose there is no charge available here. This is empty DRAM cell, and now I want to write one to this particular cell. How to do it? If we want to write one, then somehow before writing this, remember this. When we say read, data flows in this direction. This direction. When we say write, data flows from this direction. Data flows in reverse direction. So if suppose there is no charge or stored here and I want to store binary one, that means if I want to store binary one to this cell, then we have to fully charge it. So to store binary one here, first of all we have to convert this sense amplifier to stable state one. Suppose somehow if we able to convert this to stable state one, then this line will become VDD. The moment this line become VDD, just connect this switch. The moment you connect this switch, some charges will be transferred from here to here. Okay, that if we transfer some charge from here to here, that this will be VDD minus delta. And what is this? Remember, as I said, that if you want to write something, first of all you have to convert it to stable state one. So if you already converted it to stable state one, that means this is VDD and this is zero. In this particular scenario, if you switch on this transistor, then some charge will flow through this direction, and this capacitor will be fully charged. That means binary information one is already binary information will be stored here. But doing this, here the charges will be VDD minus delta, but it's not a problem. VDD minus delta is still larger than zero, so automatically again it will be it will be what is transferred to stable state one. That means VDD minus delta will be automatically converted to VDD after some time. So this is how we can read or and write to a particular DRAM cell through this sense amplifier. But again, all these things take some times. Reading from DRAM cell through sense amplifier, or writing to the DRAM cell through sense amplifier, read some time. So all these timing constraint, and what are the command required to read, what are the procedure to write, what are the different events that we have to perform, that the DRAM device need to perform to go for a read or go for a write. All these things will be explained in next class. So in the last slide, I said that reading and writing to a DRAM cell needs a sense amplifier. That means each DRAM cell must be connected with a sense amplifier to perform read and write operations. But if we see that a DRAM cell is 100 times smaller than a sense amplifier. So that's why in a normal DRAM memory, sense amplifier is designed here. That means for each cell in this particular column, there is only one sense amplifier. This is perfectly fine. If you remember how a 2D memory or a bank works, that I explained in previous slide, I said, for example, suppose if you want to read a particular entry from here, then it will activate this particular row. That it means that two rows it's not possible that simultaneously two row is activated. Either you will activate this row, or you will activate this row, or activate this row. It is not possible that simultaneously two rows are activated. So for example, suppose if you activate this row number one, you will send the activation signal to this line, then all the switches will be on. Let's concentrate on this particular DRAM cell. So this switch will on, so this charge is available to this line, and this charge will be sensed by this sense amplifier, and if a binary 0 was to, it was fully charged, then this tiny charge will be available through this. So now the charges will here will be half BDD plus delta, and here it is half BDD. So automatically it will be converted to stable state 1. In this way, the binary 1 that was stored here in form of tiny charge, that binary 1 is now available here in row buffer, and it is storing here. And now, as I said, see, now the column decoder is a different unit. In previous slides, in diagram of DRAM, I said that this is the column decoder as well as row buffer. Now the column decoder is, you can see, this is a separate unit here. So now, once this information is available here, if you want to read a particular column, for example this column, then suppose this row is available here now. So now if you want to suppose row number 1 is available in row buffer, this row number 1 is available in row buffer. Now I want to read column number 1, row number 1. So since row number 1 is already available in row buffer, now column number 1 will be supplied to this column decoder, and this column decoder will allow to pass information from column number 1 through data bus. This is how a DRAM memory works. So DRAM memory, in DRAM memory, the DRAM cell is not enough. With each DRAM cell, we need a sense amplifier, but it is not possible to assign a particular sense amplifier with each DRAM cell. That's why DRAM cell is smartly designed in this. DRAM memory is smartly designed in this way, and there is only one sense amplifier used for a particular column. So now let's revisit the main memory structure designed with DRAM. So all these things I already explained. I hope it is clear to you. This is the first picture. As I said, this is exactly how main memory or the RAMs are placed in the motherboard of a computer. Its DIM look like this, and in each DIM there are two sides, front side and back side. Both side is called a rank. Front side is called rank 0, back side is called rank 1. Each rank has multiple chips like this, and each chip has multiple bank like this. So this is how a rank looks like. And as I said, it's called rank because if we give a command here, then all the chip will perform this command simultaneously. For example, the command is read from bank 0, then all the bank 0, then all the chip will read from bank 0. So now suppose we want to read this R1C1, this is the address. That means row number 1, column number 1, R1C0, row number 1, column number 0, R1C3, R0C1. We need to read all this content or all data from all these locations one by one sequentially, and assume that the row buffer is in half BDD mode initially. That means it is pre-charged. So now, if we want to go for to read this content, row number 1, column number 1, then the first thing we have to do, we have to activate row number 1, because I said that row buffer is pre-charged. That means nothing is there. Pre-charged means it is already pre-charged. That means the row buffer, all the row sense amplifier in row buffer are in half BDD mode. So first of all, we have to activate this row. The moment we'll activate this row, all the content of row number 1 will be available in row buffer, and then read write. After activate read write means after activate all the content of row number 1 is available in row buffer, and then through this column address we have to send the address of C1, and based on this the R1 C1 can be read. Now the next is saying next content that we want to read, the address is row number 1, column number 0. In this particular case, the activate row is not required because row number 1 is already available in row buffer. So only through this line we will send the address of column number 0. The same thing is for this third address also. These two cases, the second case and third case, we only need read write operation because row is already in row buffer. If we go for the fourth case, suppose here, if I want to read or write to this particular location, then this is from row 0. And if you see, if it is from row 0, then currently in row buffer, the content of row available is row 1. The row 1 is available in row buffer. So we have to activate row 0, but remember we cannot directly activate row 0. How will activate row 0? Because if you remember, I said that if you want to read the content of a DRAM cell, then first of all the sense amplifier must be in half BDD mode. But now the sense amplifier is not in half fidelity mode. Since the content of row 1 is available here, that means all the sense amplifiers are either in state 1, state 1 or in state 0. They are not in half fidelity mode. That's why a pre-charge is required. Pre-charge means all this sense amplifier in row buffer will be converted to half fidelity mode. So first of all, we need pre-charge. After pre-charge, we need a row activation. This row activation will activate row number 0. That means the content of row number 0 will be available in row buffer. And then we can read write column number 1. So all these things is required for reading this address. Pre-charge, activate row and read write.
This slide is explaining why multiple chiefs are required in a rank. If we remember, then said that a particular rank has multiple chiefs, and the example I showed in this example, a particular rank, for example, rank zero, rank number 0 has 8 chiefs. Why 8 chiefs are required? Why instead of 8 chiefs there is not one chip? For example, here in this particular case, this rank has 4 chips, and each chip is giving 8-bit information, and that's why it is giving total 32 bits of information. Why it is not like this, where there is only one chip and it is giving 32 bits of data? Instead of this, instead of a single chip like this, why rank is designed in this format, where it is divided into multiple smaller size chip, and and each smaller size chip is giving 8 bit of information. The main advantage of this type of design here in this type of design is the lesser cost, because in this design, this with a single chip design, the pin cost is more. And if we go for this type of design, since there is number of pin in each chip is less, the cost of manufacturing cost of this particular chip is less. That's why normally rank goes for this type of design. The rank has multiple chips. Now the next question is an important question, that why we go for multiple banks inside a chip. And if you remember, I told you that all the bank in a particular chip shared a common bus to interact with outside, or you can say interact with outside world or interact with DRAM controller. So that means if bank 0 is sending some information through this line, at that time other banks cannot send information. So if this is the case, then how all these multiple banks are giving benefit? Again, if you remember, we said banks, we normally say banks are independent. So how these banks are independent if they are sharing a common bus here? And this is very interesting. Why it is very interesting? Because if you remember, what I said in the previous slide, that how a read write operation perform in a DRAM bank. And if you remember, I said there may be many steps. If this information is not already there in row buffer, then we have to go for a activation command. That means first of all we have to activate the particular row, and then all this information will be available to the row buffer. So all this particular work, this activating a particular row and moving the information from row buffer, so from the row to the row buffer, this is internal to a particular bank. This is internal to, okay, one more thing I have not explained here is, if you see, they are sharing a common bus, but don't think that they are sharing a sense amplifier also. Sense amplifier is internal to each bank. This bank has its own sense amplifier, this bank has its own sense amplifier. After sense amplifier, when they are sending the information to the outside world or through the DRAM controller, then they are using a shared bus. So in this means that the internal work of a bank, for example, the activating a row, and then after activating row, information of this row is going to the and storing to the sense amplifier. This operation is internal to each bank, and that's why this is the advantage of a bank. So suppose here, this is example of this is example where a chip has only one bank. There is not there is only one bank. So in this particular case, suppose we want to read three information. First of all, we want to read address 0, and then address 1, and then address 2. But since there is only one bank available in this chip, first of all, when we say send address, this address A0,
then it has to wait. DRAM controller has to wait up to this, or this data bus has to wait up to this. Because why this wait is, first of all, if you send a address to a bank, first of all it will activate this. After activating, this data will be available to the row buffer. After data will be available to the row buffer, you have to send a column address, and after this data can be sent through this data bus. So it takes some time. It will take this amount of time. After this amount of time, data is sending through this data bus here. After doing all these things, then only you can go for second request, because this second request may be from some other column, or maybe from other row. If it is from other row, then obviously you have to go for pre-charge, activate, and everything. So again it will go for this amount of time, and then it can send data. So if you see, if you go for this way, then data bus is almost ideal. You are not utilizing the data bus. But suppose if you go for a multi-bank design where there are multiple banks, at least assume that there are three banks instead of instead of these. So this example was for this type of design where there is only one bank. Now I'll show you an example based on this type of design. Suppose there are three banks. So now, and assume that the same three address A0, A1, and A2 we need to read. And also assume that these three address are mapping to three different banks. For example, A0 is mapping to bank one, bank 0, A1 is mapping to bank 1, and A2 is mapping to bank 2. In this particular case, here three activation command will be given to three consecutive cycle. For example, first cycle will send activation command to bank 0, second cycle will send activation command to bank 1, and then in third cycle will send activation command to bank 2. So now this is how it's work. First cycle activation command will be given to bank 0. Second cycle activation command will be given to bank 1, and then in next cycle activation command will be given to bank 2. So now, as I said here, all these banks are independent entity, and the internal operation of each bank is independent. So all these three banks will independently perform the internal operations, and the corresponding data will be available in the row buffer independently in each bank. And then hence, after this amount of time, here you can see that you can consecutively send the data after some time. So I think we should stop here. Today, whatever I explain is mostly it's a revision of my previous class. But why I covered this today, because in this week as well as the next two weeks or 2 3 weeks, we'll only discuss about the concept of DRAMs. There will be many new concept, research related advancement in this DRAM technology, DRAM memories. We'll discuss a lot of things, and for all this discussion, this basics of DRAM is very important, and that's why I have explained it again. So please take it seriously and clear all your basics of DRAM. And as I already said many times in class, that just my lectures and just my slide is not enough. You have to study it from other sources. And this time I'll share some study material in Google Classroom. Read those study materials. I'll also send a mail regarding how means the sequence, in which sequence you should read all the study material. Okay, so see you in next class. Thank you.